All right, welcome to week number 8 of AI612. This week we'll be covering domain knowledge and graphs. There is a question on Classroom to request to upload the official code for project number 1, which is taking some time because of I think the TA. So the TAs is going through some couple of claims about the grading, so they are spending their time on that assignment or that task as of now. So when we're done with that, the TAs will deal with the code request. All right. So until last week, we talked about. I mean, Tuesday last week, we kind of finished the interpretability part with the model agnostic approaches, and then the Thursday last week, we talked about concept representation or concept embedding. We talked about the continuous input and the discrete input, and when the inputs are continuous, we can rather see or visualize what the model has learned or what the model has captured about the data, more or less visually in a friendly way. But as for the discrete input, not so much. So we talked about the skipgram, how skipgram kind of lets us gain insight into what kind of concept the model has learned from the data, especially from the text side, because skipgram was developed for NLP, and then we saw how when skipgram was applied to longitudinal health records, it also did quite a good job of capturing the linear relationship between different concepts. Then after that, we've developed that into the two-layer architecture, which is MED2VEC, and then we saw how each dimension of the concept embedding could be seen as capturing a higher level semantic of the concepts rather than individual concepts. So that was the last week recap, and this week it'll be twofold. So one is domain knowledge, especially DAG-structured domain knowledge. So DAG being directed acyclic graph. So we will see DAG-structured domain knowledge and how we can incorporate that or inject that domain knowledge into concept embeddings, more or less just neural networks. Then after that, since we've covered the DAG-structured domain knowledge, which is basically a graph, we'll actually generalize EHR into a graph. So far, when we were talking about EHR, it was more or less just a time series rather than a structure. So especially for the ICU stays, where the project was using the first 3-hour amount of information, which is all time stamped, so that we could lay them out in a temporal order, and then just feed them into RNN, recurrent neural networks. So it was more or less just a time series data, or like a sensor data. But EHRs are actually a very complex data set that is like interconnected, where concepts are interconnected, and we can see them as a graph rather than just a time series data. So we'll be looking at 2 examples of using graphical structure of EHR and learning the graphical structure of EHR. All right. So so today, hopefully, we can finish covering the domain knowledge part, right? So representation learning in healthcare. So we've talked about representation learning in MED2VEC and skipgram. So how can we do better? That is the main addressing point today. So how can we do better than just simply pouring data into if you remember, when we pour data into the skipgram model for EHR, or even like MED2VEC, it doesn't really matter. Like when we use co-occurrence-based representation learning algorithm, we just simply took a lot of data and then poured them into a model, and then the model seemed to capture a latent relationship between different concepts, or maybe capture higher level semantics of the concepts. And that was purely data-driven, done in a data-driven fashion. We didn't inject any domain knowledge into it, but there are 2 main challenges when trying to do trying to pull something like that off. So one is data insufficiency, and second is interpretation. Because so data insufficiency, when we think about what we did with MED2VEC or skipgram, we took a pretty large amount of electronic health records data and poured them into and used them to train the model. So, but it's not always the case. Like all hospitals or all research organizations can possess that amount of data. So if you remember, briefly talking about the data set that was used to train Medtech. It was from Children's Hospital of Atlanta, CHOA, and it consisted of 500,000 patient records. So that is quite a lot of data. But not all organizations have that amount of data. You know, if you think about like local clinics or just individual researchers, they don't have that much data. So, so as written here, only large organizations have easy access to large data sets. So in order for the model to learn latent relationship between medical concepts in a purely data-driven fashion, we need a large amount of data. And the problem is not all organizations have that large amount of data. And even for large data sets, like in Korea, like Samsung Medical Center or Asan Medical Center, they would have a lot of data. But even for them, some diseases rarely occur. So there are some rare diseases that occur even in the large hospital organizations. So for that specific concept, it is still there is still not a lot of data. Even if the entire amount of EHR are large, for a very small specific amount, for very small specific kinds of rare diseases, it is still small data. So data insufficiency is still a challenge. And interpretation. So we did see a bit of an interpretable aspect of Medtech. We actually saw the dimensional-wise interpretability, but we are not really sure if that is actually that the knowledge learned by the model in a purely data-driven fashion closely aligns with actual medical knowledge, actual established medical knowledge. I'm saying established because like humans throughout the entire human history, like for thousands of years, medical knowledge has been accumulating, revising itself over like a long period of time. So there is established medical knowledge that has been collected for like thousands of years. So that versus that established knowledge, just by looking into the data in a purely data-driven fashion, there are two extremes basically. So we're not really sure if established medical knowledge is like is always correct, but at least we want knowledge, or we want the model's knowledge gained from purely data-driven fashion way, model's knowledge to at least closely align with what we already know, or at least doctors would like to see that. There are, I guess there are two philosophies, or it's maybe a frequentist versus Bayesian philosophy as well. But some people would like to say, data-driven knowledge gained by purely data-driven fashion way is actually the true knowledge, versus some other people say, like human intuition and heuristics and domain knowledge, those are still like, those should be the true knowledge, and data-driven practice should be used as like an augmentation to what we already know. So there are two philosophies, but at least in healthcare field, there is. I don't think we have reached to the point where purely data-driven fashion practice is enough. So we probably want the two philosophies to learn similar things. So that is why interpretation matters. So all in all, learned representation should align well with established medical knowledge. So in Medtech, we did see each dimension capturing the higher level semantics, but we're not really sure if that's correct. So it's still not, we're not really sure if it's correct. So that's the interpretability challenge, and model should be explainable as to what it's doing underneath. That's obviously true. So there are two important challenges overall: so data insufficiency and interpretation. So to overcome these two important challenges, it's rather easy to exploit established knowledge, because what we want is for the models to learn knowledge that closely aligns with established medical knowledge. So why don't we just use established medical knowledge on the get-go? Just directly inject some amount of knowledge into the model, so that the model is kind of like regularized. So let's leverage established reliable medical ontologies. So when I say medical ontologist, it's usually a hierarchical concept, hierarchical structure. So hierarchical clinical constructs and relationships among medical concepts. That's medical ontologies. It's usually represented as directed acyclic graph. So there is no loop, basically. And it's more or less tree structured. But since it's stacked, there could be multiple parents rather than like when in trees, a node can have only one parent. So things that are typical things, like popular things that are represented as DAGs are, first of all, International Classification of Diseases, ICD. So you've already dealt with a lot of ICD-9 codes for diagnoses and procedures, hopefully. And when you study ICD-9 codes, you can easily realize that it has a certain structure. So for 5-digit ICD-9 codes, there are 3-digit parents. And then for 3-digit parents, there are like grouped grandparents. So actually, for those of you who have not gone through the ICD-9 hierarchy rigorously, let me just quickly share. The screen. That's weird. Okay, give me a second. Right here. So yeah, right here. So this is ICD-9 data. If you wonder what each ICD-9 code, 5-digit code represents, you can easily come here and look it up. So for example, the popular ones are like 401.9, which is unspecified essential hypertension. So if you want to look up what 401.9 means, then you have to go through this process, like narrow down. So it should be located between 390 and 459, which is actually disease of the circulatory system. So it's 순환계 질병이죠. we 들어가서 we click this, and then we want to go into 401, this category, which is hypertensive disease, 고혈압이죠. And then there are different types of hypertensions, and there are hypertensive heart disease, hypertensive CKD, chronic kidney disease, secondary hypertension, whatever. We are looking for 401.9, so we click this one, and then now we are here at 401.9. So there are also like different granularity, like fine-grained types of essential hypertension, which is malignant, benign, and unspecified. So 401.9 is unspecified, and you would see a lot of these codes, especially for senior dataset, like dataset of senior patients. So you can see that there is a certain level, like different levels of hierarchy. So there's the very root code, and then there's the second groups, which is like the highest category, and then we go into the second highest category, and then we go into 401, and then 401.09. So there are about like 4 to 5 levels of hierarchy. The same goes for other types of codes, other types of other types of hierarchy, such as clinical. Let me actually look it up as well. Right. Hopefully, people would remember this one. This is also another hierarchy for ICD-9 disease codes. So that previously what I've shown you is actual ICD-9 disease codes, but since ICD-9 disease codes or diagnosis codes are developed for billing purposes, so which is for reimbursements and all the 이제 보험 심사 이런 것 때문에 이제 만들어진 거니까. So in order to actually use a bit more, modify those ICD-9 codes into something more clinically meaningful. So there's something called clinical classification software, CCS, for ICD-9, and we click this one, and we go to multi-level diagnosis. Then there's a mapping table for each ICD-9 code to a CCS code. So ICD-9 diagnosis code to CCS. So anything, let's look up 401.9. So for ICD-9 401.9 belongs to 7.1.1 in CCS hierarchy. So it's called essential hypertension. And 7.1.1 belongs to 7.1, which is hypertension. And 7.1 belongs to 7, which is disease of the circulatory system. So the highest category is actually very similar to ICD-9 highest category. The same. 순환계 아까도 순환계 시스템의 질병이 있었죠. 이제 요거랑 CCS랑 이제 ICD-9이랑 CCS랑 그런 면은 굉장히 유사한데 이제 밑에 부분이 이제 좀 다르죠. 아까는 이제 401.1, 401.0, 401.9 이렇게 세 개가 있었는데 여기는 지금 401.0이 어디 있을까요? 네, 여기 있는 401.0은 이제 other hypertensive complication에 이제 속해 있는. 거기에는 405들도 들어가 있죠 지금. So you can see different ICD-9 code groups are they belong to the same 7.1.2.2 other hypertensive complications. So this is also a good example of hierarchical, DAG-structured domain knowledge. And the last one I'd like to show you is something called SNOMED CT. Give me just a second. Right here. Okay, just found one. Right, so this is actually a much larger medical domain knowledge graph, or this is actually an ontology. So ontologies usually contain like entities. So their entities are the nodes, and then the relationship between entities. So like which leads to something, or which causes something, which is similar to something like that. Different types of relationships. But the CCS9 hierarchies, or CCS hierarchy, or the ICD-9 diagnosis code hierarchy, they have only one relationship type, which is parent-children. So so there's like a higher level category, and then there's like a lower level category, lower level concept. So between them, the concept, the relationship is only a parent-child relationship. But here in SNOMED CT, there are a lot of different types of relationships. So let's look up hypertension. And then there are a lot of different types of hypertension, but let's go for benign hypertension actually. And then benign hypertension, the parent of benign hypertension is hypertensive disorder. So parent and children, they are the same types of concept as what we've seen in the ICD-9 hierarchy or the CCS hierarchy. But I think there should be a bit more. Yeah, here, like finding sites. Finding site is another relationship, finding site. So finding site is where this specific problem, which is hypertensive, which is benign hypertension in our case. So benign hypertension is usually found in systemic circulatory system structure. So 순환계에서 이제 주로 발병이 된다. 예, 그런 말입니다. 네. And interprets, I guess, I'm not really sure what this is. Interprets, blood pressure has interpretation. Has interpretation increased. I guess this is has interpretation relationship is how usually this specific concept is interpreted. It could be like increase or decrease. Like hypertension is about your blood pressure being increased, right? So it's increased. If we look for hypotension, which is 저혈압, then we would find has interpretation decrease, something like that, right? I guess we can click other stuff as well. Maybe we can go for hypertensive disorder. If we click this, what happens? Disorder of cardiovascular system. Okay, I guess it's not a link actually. Right, and there are also other types of relationships, like like how the synonyms are all here. So high blood pressure, hypertension, hypertensive disorder, hypertension, hypertensive vascular. Like in English, these are all the synonyms of hypertensive disorder. So you can look, so SNOMED has actually a lot of it's a very comprehensive, super large ontology. You can find virtually anything here. You can even find for like drugs. Let's see if we can find some Tylenol. I guess Tylenol is not a drug. Acetaminophen. Right, acetaminophen. So this is I guess this is one of the ingredients of 해열제, 진통제, 이런 것들, 소염제 이런 거죠. acetaminophen. So if we click that, then there are parents, which are different types of ingredients. I guess acetaminophen has a parent, acetamide. It's a non-opioid analgesic. analgesik이 analgesik이 뭐죠? 그죠, 진통제죠, 진통제. 네. non-opioid. 그러니까 이제 오피오이드면 그 아편성 이런 거잖아요. 그러니까 이제 아편성이 아닌 진통제에 속하죠. 이 아세타미노펜은. 그러니까 뭐 보통 이제 무슨 하이드로코도닌이 뭐 바이코딘이 이런 것들이 이제 오피오이드 쪽에 그러니까 마약성 진통제고, 이제 정말 아프신 분들 드시는 요 이제 아세타미노펜은 타이레놀 계열이니까 이건 이제 마약성이 아니니까 논오피오이드 에너제틱이다. 그래서 이제 파라아미노피놀 데리버티브다, 이제 뭐 그쪽 계열이다. substance with phenol structure, 그러니까 페놀 계열, 페놀기가 붙어 있는 뭐 물질이다. 뭐 이런 것들이 다 있고, 이제 so these are the synonyms again. So paracetamol, I guess I didn't really know paracetamol and acetaminophen were the same thing. Actually, so as you can see here, there are different medical chemical structures here. There are diagnoses, there are procedures, drugs, medications. There are body sites as well, because there were finding sites. So there are body parts. Basically, everything you want to find in healthcare basically is all here in SNOMED CT. And some EHR, some electronic health records are actually recorded using SNOMED CT concept IDs. So here the concept SNOMED CT concept. So this is SCT ID is SNOMED CT ID. So this is the concept ID. So concept ID 3875170004 is paracetamol in SNOMED CT. SNOMED CT here SNOMED CT medical ontology. So some EHRs are stored using diagnosis code from ICD-9, but what I'm saying is some EHR data set is stored using SNOMED CT diagnosis ICD code, diagnosis SNOMED CT diagnosis code. So in that case, you need in order to pull those data sets together, you need a mapping table between SNOMED CT IDs and ICD-9 diagnosis codes, which there are actually, but it's not a really succinct mapping dictionary. It's actually like an N versus M dictionary. So there are some cases like that. But anyway, so if you are interested in this kind of leveraging the medical ontologies, there are a lot of them out there as well. There is like drug network. There is the chemical ingredients network. There's a lot of different DAG-structured knowledge. And actually, SNOMED CT is so large. It's actually, I find it kind of hard to actually cleverly use them, because this is like, I'm not sure how many nodes there are. There are probably like millions of nodes inside. And so if you think of the size of this graph, it wouldn't be straightforward to cleverly use them while training your neural network. But anyway, so back to the material now. Right, so that was a couple of examples of the medical ontologies. And in today's class, we'll be looking at how to use this smaller size domain knowledge, which is diagnosis code hierarchy. So it could be either ICD-9 codes or ICD-9 diagnosis hierarchy, or it could be CCS hierarchy. It doesn't really matter, because it's all like abstract concepts anyway. So the reason for using medical ontologies to challenge these two important challenges, to overcome these challenges, is one, it's a reliable source of information. So ICD-9 code hierarchy or CCS or even SNOMED, any DAG-structured domain knowledge source, like clinical domain knowledge source, is all constructed and curated by the experts in the field. So a lot of doctors has poured a lot of effort into building a very accurate, reliable DAG-structured knowledge. So it's more or less, it's a very reliable source of information. And second of all, it's the concepts close to one another are likely to be associated with similar patients. So this allows knowledge transfer among concepts. So let's take a look at an example of what I'm saying here in the second for the second point. So here, this is a subgraph of I39 code hierarchy. So as I said, there's a very like non-meaningful root at the top, and then right beneath there's the highest level of category where there was the search 순환계 시스템 질병 있던 그 레벨, 이제 요 레벨입니다. So there are infectious parasitic diseases. So 감염병, neoplasm is 종양, mental illness 이제 그 정신병이죠. So that's the underneath the highest level category. So let's take a look at the neoplasms first, specifically. So under neoplasms, there are different types of neoplasms. So there's cancer lymphatic, 이제 림프 쪽의 종양이나 뭐 그런 것들, 혈액 림프종이죠. 그다음에 이제 benign neoplasm, which are 양성 종양이고, 그다음에 이제 cancer of skin이고 이제 그 skin cancer, 그 뭐죠? 피부암 쪽이죠. So and underneath benign neoplasm, there is benign neoplasm uterus, 자궁 쪽의 양성 종양. 요거는 뭐 다른 뭐 양성 종양들. And then underneath a unspecified benign neoplasm, there is benign neoplasm column, 직장 쪽, 아니면 뭐 이제 over 이제 난소 쪽이냐. 그건 직장 쪽으로 내려오면 또 뭐가 있냐? 또 이제 benign carcinoid tumor of the appendix. 이거는 그 appendix니까 뭐예요? 그 우리가 그 병원 실려가는 거 뭐죠? 그 충수 맹장염, 그렇죠. 충수돌기죠. 충수돌기 appendix. 충수돌기에 있는 뭐 그런 류의 그 뭐 종양이냐, 아니면 이제 비넌클라 렉텀, 이제 그 뭐죠, 항문 쪽에 있는 뭐 양성 종양이냐, 뭐 이런 걸 쭉쭉 나눠집니다. So you can see that this under this lowest level captures the most fine-grained concept, and then the highest level, of course, captures the most abstract concept. So let's, for example, say that this one is a very rare disease, and this one is a rather popular, or rather, like a more prevalent disease. So this occurs rare. This is a rare one. This is a prevalent one. And if you think about it, they share the same parents. So you can think of a well-designed model can somehow learn when learning concept for all the nodes here, like they're like all the different nodes, like all different concepts. So when learning concepts for each node, you can imagine a situation where when learning the representation for this concept, maybe we can pull some knowledge or transfer some knowledge from this guy, which is a more prevalent guy, by going through the same shared parents. So the knowledge is flowing from here to here to here, so that a rather rare disease for this rare disease, we can still learn some meaningful representation by doing a knowledge transfer from different nodes. And if both are, for example, if both are rare diseases, then maybe this one is a prevalent one, so that maybe knowledge can be transferred via a shared grandparent, which is this guy. So knowledge will flow from this guy to here, here, and here, or either here, so that again, rarer diseases can still benefit from, or can still learn from, knowledge acquired by more prevalent ones. So that is another motivation for using medical ontologies or DAG-structured knowledges. So yeah, we're going to look at something called GRAM model architecture. GRAM is this is the first word actually they try to use this knowledge, DAG-structured knowledge, to inject those DAG-structured knowledge into neural networks. So let's assume that this is our knowledge DAG, knowledge directed acyclic graph. So the ones in the dotted circles are the ones that are latent. So latent meaning they are concepts, but we don't see them in the EHR. The ones that we actually see in the EHRs are the leaf nodes. If you think about it, these are the 5-digit codes here are the ones that we actually see in the EHR. For example, in Mimic3, the ones that are higher level, like these Hodgkin disease, leukemias, like the 3-digit IC9 codes, we don't see them in the EHRs. The ones we see are the leaf codes. So it's the same deal here. The leaf nodes. So the leaf nodes are the ones with like the line circles. So the leaf nodes here, 1, 2, 3, 4, 5. These are the ones that we see in the EHR. and these are the ones that we don't see in the EHR. So they are unobserved, and these are the observed. But we are going to prepare, we're going to learn the concept embeddings for every single one of them nonetheless. So we are going to learn all the concept, we're going to learn concept embeddings or concept representation for all the nodes in the entire knowledge DAG. And what we're going to assume is that the ones that we do see, the leaf nodes, are actually a convex combination of all its parents, grandparents, and also all its ancestors, basically. So there's you can think of a certain lineage. 그러니까 혈통이 있는 거죠. 혈통이 이제 맨 위에 이 가장 제너럴한 루트 노드가 있고 그 아래 이제 이 조금 덜 스페시픽하네, 그다음 더 스페시픽하네, 그다음 가장 스페시픽하네. 그래서 CI 입장에서 보면은 요 체인이 자기의 혈통인 거예요. 마치 이제 할아버지, 증조 할아버지, 고조 할아버지 쭉 올라가듯이 이제 요 일직선이 이제 체인이 얘의 혈통이 되는 겁니다. So this chain of concepts is this is a lineage of this specific concept here. So this, and we're going to assume in order to represent this guy CI, which is the one that we actually observe in the EHR, in order to accurately represent the concept of this guy, we're going to assume that this guy should be represented as a convex combination of all these concepts, all 4 concepts basically. So one here, itself, and its parent, its grandparent, its grand-grandparents. And how are we gonna derive the convex weights is basically using attention. So this is the attention weights. So alpha A comma I, A and I, alpha C and I, alpha G and I, and alpha I and I itself. So there are four different attention weights that we need to derive, for which we're gonna use a attention function, basically just feed forward neural networks. And then based on that, we're gonna based on using the attention weights, we're gonna do a weight sum of attention weight self and the embeddings of individual embeddings of the individual concepts here. So CA has a concept called EA. So this is a code, this is a vector, so vector representation. EC is a vector representation of CC. EG is the vector representation of CG. EI is vector representation of CI. So we're going to weight sum of them. So attention weights are, as I said, attention weights are generated for all pairs of basic embeddings. So the EA, EC, EG, EI are the basic embeddings. So the embeddings for all the nodes here, and its ancestors. So EI and EJ. So this is basically alpha AI, alpha IJ. So alpha AI, ACI, GI, EI, II are all derived from the simple feed-forward neural network that looks like this. And then using this, we're going to weight sum them. So weight sum them, and then we're going to derive GI. GI is the final representation. So EI were the basic representation, and GI is the final representation of this guy, CI. So CI will be, so GI from now on, GI will be used to represent CI. So GI is obtained by the weighted sum of the attention weights and the basic embeddings. So far, so good. And we do this for all leaf nodes. So CH will be represented as with GH. CK will be represented with GK, GE, and GD. So there will be a whole set of GIs, or actually, let's call them GIs. So there will be a whole set of GIs, like from G, D, GE, GK, GH, GI. There will be a whole set of GIs, and we're going to call them a embedding matrix now. So that becomes our embedding matrix. So when we do when we are going to use a lookup table, we're no longer going to use lookup table that is randomly initialized. We're going to use a lookup table that is actually a convex combination of itself and its ancestors. So when we encounter a certain leaf code like CI when going through the EHR, we're going to look that up into using this G matrix, and we're going to convert CI into a GI, and then we're going to use that for the downstream predictive layer, like be it RNN, be it CNN, whatever. Right. So yeah. So sequence of it now, as I said, when we think about a outpatient setting, a single visit consists of multiple codes, multiple medical events. So what we did in the previous in the retain and all the previous examples were that we summed them up. So basically we converted each code into a vector, and then we summed all them up to represent a single visit, right? So if you remember that. And when we're going to do the same thing here, we're going to do the exact same thing, but instead of using a randomly initialized embedding matrix, we're going to use a G embedding matrix to do that, to derive a visit representation. Yeah, so if you remember, what we're doing is here. So there was a sparse binary high dimensional vector X, so like a lot of zeros and very few number of ones, and we put it through a embedding matrix to derive a visit representation. So instead of using WX here, we're going to use G here, and that's it. So that is the only difference between regular, like vanilla EHR predictive model and the GRAM architecture model. So the only change is the embedding matrix. Right, so far, so good. Any questions so far? No? Cool. Another thing is, we've used attention weights to combine this chain of concepts to derive a final representation vector G, but we could actually, expand this to use a graph neural network, obviously. So we can actually have a stack of graph neural networks, or graph convolutional neural networks, or graph attention networks, you name it, whichever is fine. But we can use a graph, basically any graph neural networks, to learn individual embeddings for all these concepts, which is basically what I'm doing here. So the GRAM network actually just use a so it's a more restricted form of graph neural networks, because it is not pulling information from this guy. It is only pulling information from its ancestors. So it's a graph neural network with a very specific form of adjacency matrix. But if you use vanilla, just ordinary graph neural networks, then individual concepts will actually pull knowledge from all the neighbors. And when you stack one graph neural network on another, you'll be hopping, like you'll be using 1 hop, 2 hops, 3 hops, and like that. So you can see that you can view GRAM model as a very special form of graph attention networks, right? So it's an experiment. So we're gonna see how GRAM model compares against other vanilla models, and the dataset is using the Sutter dataset, because the GRAM model was, when I was training GRAM model, I was using again the Sutter dataset, the dataset that was provided by the Sutter Healthcare, which is North California-based healthcare network. And you can see, there are 2 prediction tasks on 3 datasets. Actually, yeah, I've also used Mimic3, but we're going to mainly look at the results from SutterPemp, which is a larger dataset compared to Mimic3. So 2 prediction tasks on 3 datasets. One is heart failure prediction. So we're going to use Sutter heart failure cohort, which is a rather smaller size cohort with 30,000 patients. We're going to use that for heart failure prediction, and for predicting next step diagnosis codes. 네, 혹시 지금은 들리시나요? 지금 괜찮죠? 네, 인터넷이 KT라서 그런지 이게 꼭 한 번씩 끊겨요, 집에서 하면은. All right, I'm sorry about the technical difficulties. I'm not sure if you guys watch the recent YouTube from ITSUP, all the fiasco with the KT internet and how they use QoS technology to actually limit the speed of the internet. Maybe that's happening to me as well. Yeah, every once in a while, especially when I'm using Zoom, so maybe that's taking up a lot of bandwidth, internet bandwidth, and then maybe the QoS is kicking in automatically without my knowledge. All right, so that was the unfortunate accident. Let's continue. Thank you guys for not leaving. All right, so as I was saying, 2 tasks on 3 datasets. So I've already talked about heart failure prediction, which is basically just so you can think of this as a binary classification. Heart failure prediction is a binary classification test on 30,000 patient dataset. Next one is could be a bit unfamiliar. So this is a bit like a language modeling for EHR, which is basically given a sequence of visits, you want to predict all the codes, all the diagnosis codes, particularly all the diagnosis codes that would happen in your next visit. So in language modeling, given all the word sequence, you're trying to predict the next word. But here in EHR, what we're trying to do is, given all the visit sequences where each visit consists of multiple codes, you're trying to predict the codes that would happen in the next visit, next time step. So it's a bit more like generalized version of the language modeling. And for that, we're going to use Sutter-PAMF. So Sutter-PAMF is actually a larger data, like a mother data set of Sutter HF cohort. And we're also going to use Mimic3, but maybe we can just look at a couple of examples. And some medical intelligence, as I said, you could use either ICD-9 diagnosis hierarchy, or you could use CCS multi-level diagnosis hierarchy. Basically, those two are more or less like same constructs. So they're both like tree-structured diagnosis code hierarchy. So you could use either one of them. In my experience, using CCS gave me a slightly better performance compared to ICD-9. Probably because, as I said, ICD-9 was developed for billing purposes, and CCS was a bit tuned towards more clinical purposes. All right. Oh, and if you are wondering why Mimic3 only has 7,500 patient records, it's because here, trying to do language modeling for EHR, we need a sequence of visits. So we need patients who at least made two visits minimum to do this task. So, and a lot of patients in Mimic3, they only made one visit in the entire data set. So only 7,500 patients made at least two visits in Mimic3. So that's why there is like very small amount of Mimic3. We're using only a small subset of Mimic3. The important thing, so this is a bit important. So here, the models, what we're trying to see is whether using domain knowledge actually gives you better performance compared to simply going purely data-driven fashion. So Gram and Gram Plus is the ones that use domain knowledge, and the ones that with plus here is using Glove, which is basically like a more statistical version of word2vec. So you can think of Glove as a word2vec as well. So the ones with plus, Gram Plus is the one that pre-trains the basic embeddings. So basic embeddings being this one. So basic embedding E's. So pre-training these basic embeddings for all the codes in your knowledge DAG, especially in this case, CCS multi-level hierarchy. So we're going to pre-train all the codes, all the embeddings for all the codes in the CCS diagnosis hierarchy using Glove. So and the same for RNN and RNN plus as well. So RNN is the purely data-driven fashion. This is a purely data-driven fashion. RNN plus is the one that uses Glove vectors to initialize basic embeddings. Random DAG is interesting. So random DAG is trying to use a shuffled ontology. So we're randomly shuffling the nodes in your graph in the CCS multi-level hierarchies, which means that it's a incorrect domain knowledge. So Gram and Gram Plus is using a correct domain knowledge, and random DAG is using incorrect random domain knowledge, which means just nothing. It's just random, just garbage knowledge. Simple rollup and rollup rare are more or less just heuristic driven. So we just roll up. You can think of this as like rolling up 5-digit IC9 codes to 3-digit IC9 codes, and rollup rare is a bit more fine-tuned version of that. We just roll up relatively rare codes only to their parent code. That's it. So all the codes here, like Gram Plus, Random DAG, RNN Plus, they are using 10,000 diagnosis codes only. So we're only using diagnosis codes in this experiment because the procedures and like medications, they are rather for some codes it is hard to obtain the domain DAG-structured knowledge, but for diagnosis codes there's always at least one diagnosis code hierarchy. So we're going to use that. So the feature space of these three groups are 10,000, and feature space of these two groups are rather smaller than that. So simple rolling of everything into your parent gives you 283 diagnosis codes. Rolling up rare codes, rare leaf nodes to direct parents gives you about 4,400 diagnosis codes. So hard failure prediction on Sutter HF core. So binary classification test on 30,000 patient records. And what we're trying to show here is whether using domain knowledge makes your model robust to smaller training set. So as I said, purely data-driven model requires a lot of data to correctly capture medical knowledge or domain knowledge. And not all hospitals have large data set, and even for large hospitals, rare diseases are still small data sets. So in this case, we already are fixed with heart failure, which is a bit prevalent in the United States. So this is a rather popular non-rare disease. So what we're trying to do here is actually shrink the size of the training set and see if GRAM actually outperforms all the other. And you can see that it does. So this is using 10% of the training set, 20% of the training set, 30%, all the way to 100%. And actually, it is interesting because even when we're using 100% data set, GRAM Plus is still outperforming all the other models. So you can see that you can see that 30,000 patient records is not enough to capture heart failure characteristic in a purely data-driven fashion way. That is why injecting domain knowledge gives you better performance than purely data-driven ones like RNN and RNN plus here. And sometimes the gap between GRAM and GRAM plus is smaller. I mean, sometimes the gap between GRAM groups and RNN groups are smaller. Sometimes it's wider. It depends on some data peculiarities. But the important thing is actually injecting wrong knowledge. So you can see that random DAG is the worst one across the board, like 10%, 20%, 30%, all the way to 100%. Random DAG is always the one with worst performance. We even compared to like RNN, RNN plus, simple rollup, it is the worst model. And you can see the importance of injecting correct domain knowledge. So if you're not sure, you're injecting correct domain knowledge, you should not do it at all, because if you inject random incorrect knowledge, it'll give you the worst performance. So that is an important lesson. If you're gonna use domain knowledge, you should use the correct one. This is next step diagnosis goal. So this is the language modeling for EHR. You can see that the columns represent different degrees of rarity of the disease. So the diseases in this bucket is the rarest. Disease in this bucket is the second rarest, and this is this is like more like it's like middle in the middle, and then the ones in the 80 to 100 is the most prevalent. So you can assume that hypertension or like diabetes or obesity they belong in this bucket. 그러니까 고혈압 이런 아주 흔한 질병은 여기 있고, 유전병이나 뭐 이런 것들 아주 흔하지 않은 것들은 이제 여기 있고, 그렇게 보시면 됩니다. So if we are doing the language modeling for EHR with two data sets, which is larger one Sutter-Penf and smaller one Mimic3, and you can see that for larger ones and for larger data set Sutter-Penf and for very prevalent disease in this bucket, other models for like purely data-driven fashion models, they perform as well as GRAM. Actually, they outperform GRAM, to be specific. You can see that like for the very, very popular diseases, RNN plus is outperforming GRAM, but for the rarer ones, GRAM plus is definitely outperforming all the others. Same deal in Mimic3 as well. In Mimic3, especially Mimic3 is the ICU data set, so a lot of you can see you can assume it's a lot of more rare disease would happen compared to Sutter-Penf, which is basically just senior data set. So you can see that the GRAM plus is outperforming all the other models. But for very, very popular prevalent diseases, other ones are doing just as good a job as GRAM. And again, you can see that the random DAG gives you the worst performance. So wrong knowledge, not so much here, but here is 4494 compared to 6s here. So you can assume how bad of an idea injecting incorrect knowledge, domain knowledge is. Right, and yeah, we're gonna see some visualizations of the diagnosis code representation. So just some t-SNE plus that some of you might have already seen a couple of times before this class. So using t-SNE to reduce the dimensionality of the learned, what we're gonna do is we're gonna visualize the final embeddings, the G's, not the basic embeddings. We're gonna visualize the final embeddings G, and we're gonna use t-SNE to reduce the dimensionality. Each dot represents a diagnosis code, obviously, and dot color So dot color. So there's a dot and there's a color. So dot color represents the most general diagnosis categories in CCS multi-level diagnosis hierarchy. So which means this the highest level of category. If you remember, there was like 1.1.1 and there was 1.1 and then 1. So the colors represent the 1, the single digit category. So skipgram and glove, they are not actually supervised models. So we're just gonna, they're here for reference actually, because I didn't, skipgram and glove are not among the benchmark model, among the baseline models. They're just here for your reference. And you can see that skipgram actually learns it has a better structure compared to glove. Like glove, even if we train glove for like quite a long time, all the codes are more or less randomly scattered. But here in skipgram, you can see that as I've shown you in the previous concept embedding class, you can see there are some structures, like like the gray ones are here, pink ones are here, green ones, light green ones. They're all like kind of like they seem to have certain structure inside. So compared to that, we can see how RNN, how the embeddings learned from RNN and RN plus are faring. And you can see for RNN, there are some structures at the extremes. So in the middle, it's all more or less all like mixed up together. But if you go to the far outside, then there are some structures like here, here, and here, and here. But like I would say like 80–90% of the codes are all jumbled up together. As compared to that, if you pre-train your embedding with glove, pre-train your basic embeddings with glove, then you can see that it is a bit more like scattered apart. So I'm not sure if that's a good thing though. So here, at least you could see some structures on the outskirts here, but here, not really sure. Maybe here, a hint of structures here, 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 but more or less it's randomly scattered. So compared to that, you can see Gram Plus is actually learning a very well-structured concept embedding. So here, as I said, the colors here represent the highest level of CCS multi-level hierarchy, and not just so. You can see that the codes are clustered by their colors, the highest level of colors, but they're not just that, but they are actually grouped well according to their subcategory as well. So all these codes here, all the codes 1, 2, 3, 4, 5, 6, these 6 subgroups they all belong to injury and poisoning. But all the codes here, all the diagnosis codes here, they specifically belong to a small subcategory called complications of surgical procedures or medical care. So anything related to like surgery. Here, all these diagnosis codes are related to fracture of lower limb. So when you break your leg, and all the codes here belong to other fracture of upper limb. So this is when you break your arms. So this is all thanks to using a correct domain knowledge. So if you remember correctly, all the codes, all the 5 diagnosis codes are represented as a convex sum of their chains. So that is why subcategories are also well captured in this visualization. And the same deal with black ones. The black ones are disease of the nervous system, the sense organs. So 신경계 쪽이죠. So retinal detachment. So these are all related to your eyes. This is related to your otitis. I think this is your ears, otitis. This ones are all this is hereditary degenerative. 요건 이제 그 선천적으로 이제 신경계가 이렇게 망가지는 뭐 그런 소아마비나 뭐 이런 계열이겠죠. 뭐 그런 쪽이 다 이제 여기 있고. So you can see that again the subcategories are well preserved. So this is Gram plus. So let's see what happens to Gram, and you can see the Gram is also well capturing the subcategory. Oh, sorry, well capturing the subcategories as well. So it's a bit long. It's a bit elongated. It's like a line compared to the structures here. I guess that's the same difference that we've seen between RNN and RN plus. RNN shows a bit like line looking like a cluster, and you can see that the same here as well. So maybe glove is actually scattering things around. Compared to Gram and Gram plus, random DAG is actually doing a way worse job. There are still some structures. So even if you inject incorrect domain knowledge because of the data-driven fact, because the upper layer of the random DAG is still RNN, and the RNN will learn in a data driven fashion. So this model will still capture some meaningful relationship or some meaningful concept representation, but most of them are just jumbled together, like RNN that you've seen in the previous slide. So they are the same model. So Gram and random DAG are exactly the same model. The only thing that's different is the adjacency matrix. That's it. So as I said, the CCS multi-level hierarchy is a tree, and you can represent tree as a adjacency matrix. And this one and this one is using a different adjacency matrix, and that's it. And you can see the complete catastrophe that is caused by using different incorrect adjacency matrix. All right. Any questions so far with the visualization? So yeah, this could be seen as one way to interpret or one way to check whether your concept embeddings are aligning well with domain knowledge. And obviously it is aligning well with domain knowledge because it was learned based on domain knowledge, obviously. So that is not so surprising if you think about it. What would be surprising is actually if RNN's visualization looked like this. That would be surprising. But that is maybe that would be possible if we had infinite amount of data and infinite size model. Then sooner or later, purely data driven fashion model would actually learn meaningful relationship like this. But that is usually not the case in electronic health records, at least, because we don't have an infinite amount of data. So it is usually a good idea to mix or inject your domain knowledge into your model somehow. And I've seen a lot of papers, even to like 2020, 2021, a lot of papers that try to mix different types of domain knowledge into your model for predicting diseases or maybe recommending drugs, something like that. We'll talk about that later. All right, so since this is a attention model, it would be interesting, or it would be insightful. It would give you a bit of an insight into what the model is doing if you study the attention behavior. So this is the attention behavior analysis, studying how Gram assigns attentions to the nodes in the DAG. So what we would like to see is if the attention weights here, the alphas here, if they're actually working correctly as we expect. And what do we expect is right here. So there are two criteria. So we're gonna analyze the attention behaviors for 4 diseases. So I'm choosing 4 diseases based on 2 criteria. So whether the disease is rare or frequent. So 이 흔한 질병이냐 아니면 이제 희귀 질병이냐를 가지고 한번 나누고. And then another criterion is few siblings versus many siblings. So some disease might have a lot of siblings. So sharing a same parent, there could be like million different siblings, and maybe some diseases might have only 1 or 2 siblings sharing the same sharing the same parent. 그러니까 이제 그 자기 자매가 이제 여기 하이라키가 이렇게 있잖아요. 하이라키가 이렇게 있으면은 얘의 자매는 이제 얘가 되는 거고, 뭐 얘의 자매는 얘가 되는 건데, 이제 어떤 질병은 자매가 이렇게 보면 딱 하나밖에 없는데 어떤 질병은 자매가 뭐 한 수십 개 있는 경우도 있거든요. 그래서 그렇게 나눠보는 겁니다. So okay, as I said, 2 criteria: rare versus frequent, few siblings versus many siblings. And according to this criteria, we have 4 diseases. So other pneumothorax is both rare and it has few siblings. So and essential hypertension is super frequent, but it has few siblings. Joint order disorder, it is rare disease, but it has many siblings. Need vaccine for flu. This is actually this is not a diagnosis code or disease. This is more like for billing purposes, but still it is part of ICD-9 diagnosis code, or actually CCS diagnosis code as well. So need vaccine for flu is both frequent, it has many siblings. So there are 4 types, and let's see one by one. So here are 4 representative diseases. Leaf nodes, so the leaf node here represents the disease. Upper nodes are the ancestors. Size of the nodes, so there are different circle sizes. Size of the nodes show the amount of attention it receives. So the larger circle means it is receiving larger attention compared to the smaller circles, and it is also shown by the bar charts here. So the larger circle and larger actual attention weights. So if you sum these 4 bars, it will sum to 1. And number in the parentheses. So number in the parentheses here, 1, 2, 40K, 9K. They indicate the frequency of the disease in the training set. So this means that other pneumothorax occurs only once in the training set, and that is it. And we exclude the root node from this. So actually there are 1. So this is other pneumothorax. There's a parent, grandparent, great-grandparent, and then there should be a root node at the great-great-grandparent, but we're just going to ignore the root code because it's just meaningless, because root node doesn't mean anything. Right, so if you look at this, other pneumothorax, as I said, other pneumothorax is rare and has few siblings. So it has, as I said, only once does it occur in your training set. So it is super rare, and it has only 5 siblings. So there are 1, 2, 3, 4, 5 siblings. So there is not much to learn from your siblings as well. So you can see why the model is putting a lot of attention on great-grandparent. So 70 to 80% of the attention is pouring towards the great-grandparent here, and only a small amount of attention on the parents. And this amount is, so it is a weight sum by this amount of attention with the basic embedding ease. So compared to that, you can see here, this is also very rare disease. Only twice does it occur in the training set, joint disc disorder, but it has a lot of siblings. It has 139 siblings. So there's like 139 siblings all the way here. And you can see that is why a lot of attention is being poured towards its parent, because there are a lot of siblings, and some siblings might be really frequent, might be really prevalent. So there could be a lot of things to learn from that sibling, right? So via the parent, because it's an indirect knowledge. So that is why a lot of siblings could provide a lot of knowledge to the parent, and then the parent will give this knowledge to the rare ones like this guy. So you can see that happening. Compared to that, so the third one is essential hypertension. So you can see that it is occurring 40,000 times in the training set. It is a super frequent disease, which it should be like 401.9 or 401.0 or something like that. And it has only 2 siblings. So there's only 1 and 2 siblings sharing the same parent. And that is why most of the attention is pouring towards itself, the essential hypertension itself. This is basically self-sufficient. There are already 40,000. The model has seen 40,000 times of essential hypertension in the training set, and it has only one sibling. So it doesn't need to rely on anything else. It just needs to rely on itself. So that is why I'm saying it is self-sufficient, and that is why the attention, like most of the attention weights, are pouring towards this guy. Compared to that, need vaccine for flu. This is occurring 9,000 times in the training set. So it is more or less pretty frequent, right? 9,000 times in the training set, and but conversely to this, it has a lot of siblings. It has 103 different siblings. So there are a lot of siblings, and similarly to this guy, a lot of siblings would provide a lot of knowledge to the parent, and that is why the attention is a bit more poured towards the parent as well as itself. So it is as self-sufficient as this guy, but still there is something to learn from the parent because of the high number of siblings. So that is why the attentions are a bit shared towards these 2 nodes. So you can see that it is more or less working as we expected. So the rare ones, for the rare diseases, we would like the final embedding G to be pulling information from one of the parents, and then for the frequent ones, we would expect the final embedding G to pull information from itself mostly, and that is what we're seeing here as a pattern. Right. So, any question? You would see exactly this kind of behavior if you had used graph attention network as well, but graph attention network wouldn't be using only its ancestors. It would be using siblings as well. So that would be more expressive, but then it would be harder to analyze the attention behavior. Right. So no question here. That's cool. Right. So the conclusion is leveraging domain knowledge improves performance. So we've done we've looked at two data sets. No, actually three data sets. So we've looked at two prediction tasks for three different data sets. One with large Sutter-Penf data set, one with small mimic3 data set, and one with like medium Sutter heart failure data set. And across all data sets, across all tasks, Gram and Gram Plus actually outperformed all the other models, especially for rare diseases or for smaller training set. And visualization and the attention behavior actually kind of, I wouldn't say rigorously, but empirically indicated that the model was capturing domain knowledge as well as we expected. So as I said, healthcare is abundant with domain knowledge. I think it's especially for the case of healthcare because of all the administrative works and the billing purposes and all the research done over like a lot of years, like over decades. There are a lot of domain knowledge to be gained, to be utilized or exploited in healthcare field. And we've only looked at diagnosis code hierarchy in this example, but as I said, there are SNOMED CT, which is way more comprehensive. It has diagnosis, has body part, it has medication, it has procedure, it has everything. I mean, chemistry as well, it has everything. If you're interested in using subfield, like subcategory of the domain, healthcare domain knowledge, there is something called CPT code hierarchy for procedure codes. So procedure being, X-rays or operation, surgeries, or ventilation. 그러니까 시술이죠. 시술. 그러니까 이제 뭐 수액을 맞거나 수술을 하거나 뭐 이런 것들이 다 이제 시술에 해당하는데, 이제 그거를 위한 그거용 하이어키도 따로 있습니다. CPT 코드라고. 이 CPT 코드도 사실은 이제 빌링을 위해서, 그러니까 이제 이 수가, 이 보험 처리하고 나중에 이제 이 심평원에다 제출하기 위해서 있는 그러기 위해서 만들어진 건 마찬가지인데, ICD-9은 똑같은데, 어쨌든 얘도 하이어키가 있어가지고 이제 어떤 CPT 코드를 보면 걔의 부모랑 뭐 조부모랑 이제 뭐 증조할아버지, 뭐 고조할아버지 다 알 수가 있습니다. So you can, if you're interested in using procedure code hierarchy, you could use CPT code hierarchy. And if you're interested in using drug-related information, then you could actually use a lot of drug networks. There is actually, maybe I can look up some drug networks as last example. Let me see. I remember seeing, give me just a second. Let me see. Right. All right. Let me see. Yeah, there are some couple of examples. I'm not sure if this is the right one, if I remember correctly, but There is something called PubChem. I guess this is not exactly a drug network or drug relationship network, but this is actually, you can there are a lot of chemical structures. This is chemical structured actually database, so you can just look up what some of the popular examples as well. So acetaminophen, paracetamol, which is the same thing. There is like a lot of meta information here, and then the I'm not sure if we can click this. Right. So there's a lot of meta information. There's unstructured text information as well. So how it is used, and should be, yeah, related records, spectral information, chemical vendors, toxicity, safety and hazards. Let's see. Right. So there, yeah, this is like a very well-structured, very comprehensive data set. So this wouldn't be particularly useful if you're only interested in drug information. But this is, as I said, a very comprehensive data set. So if you can somehow download the information from this, like Wikipedia dump, there should be like a PubChem dump. And if you can use that, then you can, when you're trying to like recommend drugs to the patient using EHR, you can actually incorporate this into your prediction model, and then try to see if what you're trying to predict has adverse drug interaction. Like if it would be bad idea to prescribe 2 medicines at the same time or something. So that could be one of the examples of using drug networks. Oh, that was actually a question. Question from Soto. So okay, I'll just conclude the drug related example like this, and let me get back to the slides. And question from Soro was, what are the current state of the art deep learning methods for domain knowledge in healthcare? Deep learning methods for I would say it's more or less using variants of graph neural networks. So a lot of, as I said, a lot of knowledge are structured knowledge. And if they're not structured, actually, they're not really, it's really hard to exploit them in a well-engineered manner. So if, for example, there are a lot of unstructured knowledge in the world, like, you know, there's a lot of medical textbook, for example. So so yeah, if you're like a medical student, then you would be reading a lot of medical textbooks. So if we can somehow exploit that and then inject that knowledge into your model, that would be, you know, that would be great. But usually it's way more easier to inject structured knowledge because first of all, EHR are structured, electronic health records are structured, and they have all the codes and everything. And if you can find a domain knowledge, structured domain knowledge that shares the same code as the ones that is used in the EHR, then you're just good to go, right? So you can just simply incorporate them using graph neural network or its variants, graph attention network, graph convolution networks, whatever, graph information bottleneck, whatever you want, just any graph neural networks, and then you can just try to maximize your predictive accuracy somehow. So that is more or less. A lot of papers that I've seen are different kinds or different variants of that approach. Other than that, actually, if you're interested in like drug development or that kind of stuff, or adverse drug events, some people use like, you know, chemical knowledge even to that level. Like, you know, it's so like the drug level knowledge is not enough. So if you want to, you know, do like protein interaction or, you know, like RNA, DNA, that kind of stuff, then you need a lot of biological domain knowledge to inject that into your model, right? So people who has like biological background or biochemistry background there, and who has like some knowledge in machine learning, they try to inject their knowledge into the machine learning model and then try to, you know, predict some kind of like molecule activity or molecule behavior. So that is way more specific to biomedical or bioinformatics domain rather than AI domain, right? Hopefully that answers your question. All right, so I guess this is the end of today's topic. Okay, so thankfully we did cover all of them, and then next week this Thursday, we'll look at how we can interpret EHR itself as a graph, and then how to use that graphical structure, or how to learn that graphical structure. All right. Okay, thank you guys, and I'll see you guys this Thursday. Bye-bye.